Support. Okay. It is working. Okay. So I think I'm going to introduce myself. I'm the session chair and the presenter, and soon enough, who knows. Okay, there you go. So we thought that it would be also interesting to introduce to you a little bit the type of research that we do inside Telefonica Digital. And with that opportunity, I have to say that tomorrow we have the pleasure, and we managed to actually get to come and talk here, the Director of Product Development and Innovation of Telefonica Digital, Carlos Domingo. His talk is going to be at 8:30 in the morning, which is a little bit challenging, I think, for a lot of people, but one of the things that Telefonica has done recently is reorganize to try to tackle the internet challenges and the cannibalizing that people have actually mentioned in the past 4 talks. And I think Carlos has a unique vision that would be interesting to share with you. And we managed to get him here, so it would be greatly appreciated if you made the effort to be here at 8:30 for this. With this, I'm the recent head of the Internet Systems and Wireless group. I've just joined Telefonica 9 months ago, actually. So this particular talk is going to summarize the work that the research group in Barcelona has done within the space of Wi-Fi. And Wi-Fi for telecommunications operators typically is seen just for offloading. So when you have a lot of data traffic and you don't want to congest your spectrum, you just offload it to Wi-Fi access points that you spread across a space. So the research group itself, and I'm representing the work, all of those people that are mentioned below, is to try to see whether Wi-Fi gives us unique opportunities that may go beyond offloading itself. So let me see if I manage to convince you that it does. So first of all, I don't think anybody of you would disagree with the fact that Wi-Fi is everywhere. You can see it in hotspots, you can see it in houses, you can see it in centrally deployed systems like what telecommunications operators do today by placing hotspots all over the place in order to do the offloading capabilities that we mentioned before. So this means that there are urban areas where you can see a large number of Wi-Fi access points, and I think this was one of the points that somebody made before about Barcelona. There are cases where from within a particular home, and I think Jonathan made this point as well, you may see 25, and this probably is an average case. In some cases, you may see 40 or 50 access points within range, especially in very densely populated areas with apartment complexes, etc. So telecommunications providers, and I think all telecommunications engineers, typically when they see this large number of access points, they think, oh my goodness, this is not a good thing, interference may come up. And I think somebody mentioned this morning that, they have a nice Wi-Fi network, but they end up using 3G inside their house just because interference is not allowing them to do anything useful using the Wi-Fi frequencies. So this is one facet of the extreme Wi-Fi density in urban areas today. But also there are some companies in the recent past that saw this as a great opportunity, and this, here I'm taking one particular example of a Spanish company which is called FON, where they started selling Wi-Fi access points with dual SSIDs, allowing users easy roaming across densely populated areas with large number of phone-subscribed access points. So in this particular case, if you're a phone subscriber, you could actually sign up to a service that says, I allow every phone subscriber to use my own access points, but in response, I'm going to use all other phone access points as well when I roam in areas that I don't have coverage. So this is one aspect of the great density and the opportunities it allows. Here in this particular case, we have roaming. So Wi-Fi is not only used because of the fact that it allows you wireless access, but it also because it enables very large speeds. And as the new Wi-Fi standards evolve, these speeds are going to be greater and greater. The problem that we face inside the house, however, is that while the wireless speeds are very high, the wired speeds are still pretty much on the low side, or in comparison, they are not as high as the wireless itself. So one could imagine that in the 21 megabit per second Wi-Fi connection, if you were to do anything that has an internet component in it, you cannot really saturate that throughput since your DSL connection is going to be the bottleneck. So in the academic community, when we saw this discrepancy, and I put myself in the academic community because we are a little bit in the barrier between, the threshold between academia and industry in the research labs, they saw this as an opportunity as well. And they said, given that there is this discrepancy between the wireless throughput and the wired throughput in residences, what if you could connect to multiple access points that may be within range and basically download from each one of them, trying to basically get this 21 megabits per second total, which means I'm going to aggregate those 3 different wired connections in order to improve the user experience, improve the throughput. And here, this falls into the user experience and the quality of experience simply because we are trying to allow the users to do something they could not do before and enable services that they couldn't consume before. So work from Microsoft Research in Redmond in 2004 actually showed how it's possible to use a single wireless card to associate with multiple access points at the same point in time. The idea is that they used TDMA access, and they basically fooled the 802.11 protocol in some way. So the point being that I'm going to associate with a particular access point, I'm going to download whatever I can, saturating its backhaul. Then I'm going to tell the access point that I'm going to sleep. That access point is not going to tear down my connection because this is what is typically accommodated in power saving mode. I'm going to go to another one, do the same trick. And this way, I can basically fool all the access points to believe that I'm in power saving mode while I go to different frequencies and potentially different access points to download data from. So is this clear? So that was actually, this is something that was first proposed by Microsoft in 2004. I recently found out that Windows 7 is actually supporting this capability in virtual Wi-Fi. So you can actually do this from a wireless laptop today if it uses Windows 7. And here is the animation that basically shows that I can download from all the access points at the, in sequence while maintaining connections with each one of them. So this essentially enabled the capability of connecting to multiple access points at the same time, but it doesn't really address the issue of how efficiently can I actually do this. So there are many different ways in which I can associate different access points and different amounts of time. I can stay with each one of them. So later work that appeared in a different conference, basically from MIT, and actually one of the people in this paper is going to be with us tomorrow. They tried to come up with a scheme that says, how can I actually maximize the amount of traffic I can download in this way? Because different access points are going to have different wireless qualities and different backhaul capacities. So it's not a trivial optimization problem to say what is the maximum I can get given the set of access points I have in range. Okay, so now this was prior research because before we entered this particular area, we have managed to virtualize the wireless card and we have managed to optimize the amount of information we can download from multiple access points within range. We are a telecommunications provider, so the research group were tasked with the question, can this actually work in practice? Because this would make a terrific service. Telefonica has probably a 60%, 70%, maybe Cayetano knows, penetration in Barcelona. You could imagine that there are many different Telefonica access points within range of every single Telefonica access point in Barcelona. So what if we manage to provide a service of that sort that doesn't only allow roaming, but it can also allow higher speed capacities, right? Because now you are operating beyond the limitations of your own ADSL connection. Even though you subscribe to 6 megabits per second, you can get 21 megabits per second when resources are available at the back end. It's a pretty attractive proposition. So you have multiple access points and you can aggregate their capacities. And the answer that we found was actually, if you do a little bit, if you think carefully about it, the answer is no. And the reason why is that the previous schemes, the way that they were designed to maximize the individual throughput. And given that each one customer is going for its own maximum benefit, you can imagine situations where this may lead to unfair situations. And maybe this can be perceived as an academic exercise on our part, but for a telecommunications provider, when you deploy services of that sort, you need to have sorted some things out, such as, you need to have equal service to the people that pay equal amounts of money. And you need to be able to ensure the fact that you are going to maintain your business. And I'm going to show you the two parts here. And here, one of the inventors is in the room. You can spot him if you want, but we have animations of the problems that you may have when some users get more than what they subscribe, and some others, they get a less share, a smaller share of the available resource. Okay, I think it's stuck. Okay. So consider this particular case where you have 20 megabits per second wireless LAN, and each ADSL connection is 5 megabits per second, and you have two different stations. One of them is able to see 3 access points. The other one is able to see just 2 access points. If you go for maximization of the throughput alone, then the person on the right is capable of aggregating capacity from 3 different access points. The other one is able to aggregate just from 2. So in this particular case, on the right-hand side, you see the topology and fairness. Depending on how many access points you have around you, what are the wireless conditions and the wired capacities, the station A can get much more throughput than station B in this particular case. So users poorly located will observe greatly reduced throughput with respect to better located stations. A second problem, today's applications do not generate just a single flow. So what we observed is that in some cases, like when you run peer-to-peer application versus you run a single browser, if you have multiple flows, you get more resource. Again, some people get more than their fair share than others. So people are unhappy. Another interesting and more fundamental, I think, problem in this type of approach is you may have billing unfairness. So now you have station A on the right that has paid for a 10 megabit per second DSL connection. You have station B on the left that has paid for 1 megabit per second connection. If they share the resources of their neighborhood, like the access points capacity in the middle, then you may have tragedy of the commons, with the point being that the station B, while they have paid for 1 megabit per second link, they can get much more than what the other guy on the right-hand side. So you need to ensure that the benefit that both users have is proportional to the resource that they actually offer inside the network. So our goals here was to increase the speed of internet connection by aggregating WLAN backhauls with benefits for all the users without incrementing network costs for the ISPs in a completely distributed way and making it commercially viable. One of the things that you don't want to do is basically provide a service that encourages all the users to downgrade the capacity of their DSL plan, right? Because if they know that they can actually aggregate capacity from everybody else around it, why would I pay 10 megabits per second given that I can take it from the neighbor for free, right? So the team in Barcelona actually built a prototype, complete working prototype from the transport to the physical layer, and we have a publication with all the details in one of the premier conferences in networking. I would be happy to provide you a pointer to this. And then we tested it in the lab in Barcelona under realistic conditions. So this is the floor plan of the previous lab that the group was located. And we did a few experiments just to see if it actually achieves the goal of fairness and if the resource allocation across users is proportional to the resource that they offer in the network. So the effect of location here, we have a particular station A that is in a very good location, a station B that doesn't have as many access points around it, and we are also making the access point, the station B to move away. The major points that you need to take out of these plots are the following. See here on the x-axis, and suddenly all the tags disappeared, but anyway. So x-axis is time, and what you do not want to see, so the blue line is the throughput that the blue station receives, the green line is the throughput that the green station receives, and the red line is the aggregate. In the affair situation, you will see this gap between those two lines. In the case of our own prototype, you see that both lines are actually at the same level, which means that we are actually offering fair service regardless of the conditions of the two stations. Even when the station B moved, you can actually see it, that eventually it converges to the same rate for both users, which is what we were aiming for. So in the second case, what we tested is different applications and different locations, as well with the lower grade service. So the station C has a lower throughput subscribed in its DSL connection than the others. Again, very simple, especially given the visuals. what you want to do here is you want to see the green and the blue line at the same level, because these are the two stations that have subscribed to the same ADSL plan. And regardless of the conditions, they should get the same allocation of throughput. The red line is the station that was subscribed to a smaller plan for ADSL. And in this particular case, of course, you don't want to give him the same resource, the same throughput as the guys that have paid more for the DSL connection of higher speed. So he gets the fair share according to the rules that we have imposed in the optimization algorithm. So now, because I'm the speaker and the session chair, I have to time myself. So this looks pretty good, and we think it is a very viable case that makes Wi-Fi much more attractive than just for roaming, especially in areas where it's highly dense. There are opportunities beyond the negative impacts that people see. You can have two users that are very happy despite the density just because they can aggregate throughput whenever throughput is available. Okay, so we are not going to saturate links that are being actively used by their own user. We are just going to use the spare capacity available to augment the service that subscribers have inside their homes. So this was the first part, and I'm going to conclude towards the end, giving you a little bit of food for thought, is that in this particular case, what we did is we use a single wireless card to connect to multiple access points, and we can download at higher speeds than our own individual connection. So now we see also the other side of the coin, and here's one thing to think about. So in most cases, when you look at home computers, they are not always doing things, right? One, if you were to monitor the utilization of your ADSL connection, you rarely use it. During the night, it's pretty much idle, except from a little bit of traffic, that any device that may be on may be generating in terms of heartbeats. So utilization of residential gateways is actually pretty low on the average. So when the idea here is that despite the fact that those devices do not really do anything useful per se, they still consume a significant amount of energy. It may not be significant in the sense that they compare with data centers on the internet, but still they are continuously on, and their use is not proportional to their energy consumption. So here we were thinking, if indeed the load on a home gateway is low, and you have this kind of cooperative schemes that allow you to communicate, to connect to other access points in your vicinity, one thing that you could do is you can direct light traffic to your neighbor, and then you can turn yourself off. This means now that your residential gateway is off, it saves energy, and it potentially saves energy, as we will see later on. So now, so direct light traffic to a neighbor gateway, and you let your own home gateway go to sleep. When that station on the other gateway goes away, which means now the residential gateway on the right is not needed because there is no home computer connected to it, you're of course not going to use the power of your neighbor to have your own computers connected to the internet. So what we can do is we can look for another neighbor that could sustain this light load and turn both of them to sleep. And you can see how these kinds of algorithms could actually work. Whenever you see that the particular gateway is getting overloaded or its own owner requires more resources, you can basically put things back as they were, trying to basically shuffle the traffic in the neighborhood while trying to maximize also how many gateways sleep at each point in time. So again, we have two very happy users because now they can connect to the access point in the middle, and they can have their own gateways go to sleep, which means that they save energy as well. One additional point that this solution brings in mind is that if you manage to turn off a significant number of residential gateways, then you could also have the potential of turning off entire line cards at the DSLAM part of the network. Think of DSLAM cards that may sustain, that they may hold 32 to 64 customers at a time. If you manage to do the aggregation in a certain way so that you can turn off entire line cards, you don't only have a significant energy savings for the users themselves, but also for the network as well. And we did evaluate this as well. So the point that we try to make is that this type of paradigm could actually enable energy efficient operation of access networks that scales according to the demand of its users. And we did get an actual DSLAM from the Telefonica Spain network, and we actually tested this in reality just to see if it makes sense, and it does really make a lot of sense, but it requires the installation of additional equipment, which are switches that are going to be able to pack the on ports in a small region so that you can turn off line cards, because if you expect line cards to turn off randomly, they would not all collide on the same line card, right? You need to push all the on ports in a smaller number of line cards and turn the rest off. So there is a little bit of investment to be done here, but this is one of those things that operators could be very interested in, especially given the consumption numbers that access networks have. So we did build a prototype again based on the previous work. You know, there are very simple modifications you can make to make this work in this fashion as well. And here we are showing you across time the number of sleeping access points that our solution could achieve. So with the blue lines, we have the sleep on idle. What if you were to allow the access points or the residential gateways to sleep on their own after, say, 30 seconds of inactivity, which is something that a lot of equipment in homes can do by itself, versus our solution, which we call BH square. And you can see that the number of access points that we can turn off in residential gateways is much higher, just because we are able to aggregate the load on a small number of access points. You may think, you know, that this is a simple task, but a lot of the applications on the internet, they are pretty chatty. So even if your laptop doesn't do anything or your phone doesn't do anything, it's going to go to Facebook to try to see if there is an update every 5 minutes. So these kind of inactivity timeouts may actually be violated by very small bits of traffic that tend to keep the residential gateway active all the time without any meaningful information actually being transmitted. You know, you may have Twitter feeds, Facebook feeds, your mail may be pushed every so often, you may be checking servers for status updates and all that stuff. So, and what are the savings for the ISP? And this is the last slide. So here, this is a little bit busy. The lines I want you to focus on are the blue line and the red line. So the blue line shows what energy savings you could have if the residential gateways had a sleep on idle mode that was respected across the entire network. And there you see that you get 20% approximately energy savings. Now, if you manage to aggregate traffic on a small number of gateways and have those switches I mentioned before that are capable of packing the on ports in the smallest number of line cards, then you can get 40 almost % energy savings, which is a quite significant fraction of the overall energy that Telefonica spends on powering on these devices. So this is the type of research we have done with Wi-Fi. One of the nice things that we found out as we started looking into this aggregation of wired backhauls is that we are capable of allowing roaming. We are capable of enabling higher speed downloads. But also one of the nice things that came a little bit, you know, we realized afterwards is that you are able to enable better coverage inside the house just because you allow the user to connect to any Telefonica access point around it, right? There are specific houses where users may not have equal coverage across the entire space. By having this kind of solutions, you are basically able to give the best performance possible across the entire house just because you are flexible with respect to where the laptop or the desktop or the handheld is going to be associated. Now, one of the caveats that I haven't mentioned so far is that this type of approach relies on modifications on the client Wi-Fi implementation. And while we started with these approaches because we thought, you know, okay, we don't need to change all the equipment, all the access points, all the residential gateways in the network, it comes at a cost because the variety of devices that have Wi-Fi interfaces today is quite high. So if you really want to enable this, you need to modify the Wi-Fi driver for the iPad, the Wi-Fi driver for the Mac, the Wi-Fi driver for the phones, and this comes at a great cost. So right now we are looking into solutions that could enable this kind of usage models, but only from the access point or the residential gateway itself, since it allows you a much smaller set of devices that you actually need to modify to enable this. With that, I have to also mention that we are currently piloting this type of technology in South America in 300 different, with 300 different people, just to see, you know, how users appreciate the gains, if they appreciate the fact that they get higher throughput, better coverage, and the ability to roam. And if all goes well, hopefully, you know, this will become something that people may use in their houses soon. With that, we believe that Wi-Fi has further uses than just offloading. Offloading is the simple, very tangible benefit, but we think that it has many other novel uses that we can exploit. But fairness is a crucial factor for commercial deployment. And the solution that we have, which is called Themis, successfully provides this in such scenarios. In addition, in cooperative environments, Wi-Fi virtualization can lead to further benefits like energy-efficient operation of the network, the residential gateway, and the APs. And maybe you have even more ideas as to things you could do in cooperative, highly dense Wi-Fi environments like the ones we face in urban areas. So that's it from me. If you have any questions, I can.
I'll take the first question. I'm a big believer in Wi-Fi offload, but you mentioned that you need to change the Wi-Fi device driver. How about if you need to actually change also the 3G device driver, the modem, the 3G modem device driver, right? Because you need to support seamless and intelligent handoff between 3G or whatever is, your radio protocol, your radio modem, and the Wi-Fi, right? So to get to the point where we have real fully integrated Wi-Fi or alternate access networks fully integrated with the wireless infrastructure networks, we need a few more things, and that's a question. What does Telefonica do, for example, about the need to bring the Wi-Fi traffic inside your core network to support seamless handoff, session handoff? You need to do that to be able to monitor what the user does, right? And if you do that, you increase the signaling that now you have to load on your MME or your
I think Cayetano wants to answer this question.
And so on and so forth, right? So it comes at a great cost, but also at technical solutions that are not quite there today.
I see. So Cayetano, you wanted to make a comment, no?
Yes, just for clarifying what we're doing for bringing back the traffic of wireless LAN. We're planning to do so. We are not doing that. The business case is difficult to fly in a short-term basis. I mean, where's the money you will do of bringing all the traffic that is huge that you have in the Wi-Fi to the network? There are products available. There's a 3GPP standard, it's high wireless LAN. And we have even a selection process for implementing this type of solution, but we haven't implemented yet. Okay.
Yeah.
Okay. So thanks a lot for the presentation. My name is Juan Carlos Zúñiga. I'm with Interdigital. I have two questions regarding the prototype and the setup you presented. The first one is to do the MAC aggregation, you should have kept an IP anchor, I guess. So all access points should be somehow connected to a concentrator type of box so that you can then split the traffic without disrupting the TCP session. So, so I guess that was one requirement. Well, you were saying
so we are using tunneling, and actually this is one of those things that has taken the longest in the pilot right now to get all the infrastructure inside the network to do this effectively. Okay. You're right. Yes.
And the second question that I had was, how do you take into account the difference in uplink and downlink since 802.11 is at the MAC level? It takes any STA, and for that matter, the AP is also an STA into account the same way. So they all have the same access to the channel. So how can you actually split and go to sleep, taking into account the asymmetrical division of the uplink and downlink in a fair way?
So right now, this trick, I think, is applied to downlink alone, just because when you go to sleep, you ask the access point to buffer packets for you and not drop anything until you come back. But uplink is a whole different beast. Okay. Right now, I think our observation is that we have a solution that works pretty well for downlink simply because downlink is the primary source of traffic that we see in networks. But you're absolutely right. I mean, uplink, I don't think anybody has a very good solution anywhere. Right. Even the standard itself is not able to control graphic uplink.
Correct. Thank you.
No, you're absolutely right. Okay, I'm the session chair. I have to keep track of time. So one more, and maybe then we can go to discussion, and you can have questions for all the speakers. Yeah.
So my understanding is that you're probably using the power save scheduling feature in the 802.11
Yes.
to fake that access point has to wait until the guy wakes up, right?
Yes.
If more and more devices start doing it, what impact does it have on the delay performance as well as the buffering requirement at the access point? Because that definitely will be linearly increasing with the number of active users trying to use this kind of feature. Is that a fair statement?
Let me think about it. The way that we use it, if the access point starts dropping, you are going to take it into account in the calculations anyway. So I'm not sure that it's going to increase the buffer requirement.
If I have connections to 3 different access points, right? I receive it from one guy, then I tell him that I'm going to go to sleep. Effectively, during that time, when I'm visiting other access points, this first one is buffering my traffic if it's coming down, right?
Sure.
So if more and more users start doing it, this guy who has this buffering going on, he has to do it for all users that he has already served, right?
So eventually, I think there are going to be drops, and the system is going to adjust, right? So you basically capture the performance you receive from each individual access point, and the clients are going to split. They are going to adjust their TDMA cycles appropriately so that they do not face poor performance. Okay. I think that's the benefit of having a distributed approach. It's capable of adjusting to the conditions itself. I don't know, Eduard, do you have a better answer for this?
Can I elaborate on that? Because I think that's a very important point. But I thought that when you talked about switching from access point to access point, you meant at the level of flow.
At the
level of flow or session. In other words,
No. Through. Every flow is pinned so that you don't introduce, reordering and negative effects that may impact performance.
Then you need to have an end-to-end solution. I mean, if I stream a video, right, then it becomes, how am I going to stream my video through another access point? The content side has to be aware of that.
So actually, that's what the previous gentleman asked. We use tunnels that are going to terminate this within the network, and then the rest of the connection just flows as is, right? So we are basically introducing tunnels, and we bridge that connection with the content server eventually.
Okay, so there is the network component.
Yes, there is a network.